Okay, so we are discussing the debris in the solar system. Last time we talked about asteroids and also meteoroids, meteors, meteorites, right? 3 possible stages in life of meteoroid. Today I'll talk briefly about the comets. Unlike meteors, there are just flashes of light that, if you don't look, you miss it. Comets are visible for a few days and sometimes even a few months. And there was recently one at the end of November that was barely visible from where we are. But they hang around for a while, so you can view them. And as you can see on this photograph of a comet West, there are several features that every comet has. You have this head called coma, and inside the coma, which is quite extensive in size, there is a nucleus which ranges in size from maybe 1 kilometer up to even 40 kilometers. Recently, they managed to photograph one that is 40 kilometers across. Then there is ion tail that is not as bright as the other tail, and it always points directly away from the sun. And we talked about that before. It's basically light pressure. Photons carry momentum that can push on the stuff. So the light pressure moves this material that evaporates from the comet away. And there is also dust tail that, because its particles are more massive, they actually move slower, and as a result, it is slightly curved. So the ion tail is always pointed directly away from the sun, and the dust tail has a little bit of curving. There are 2 types of comets. Most appear once at totally unpredicted times, and they are called non-periodic or long-period comets. So that's one group. And then there is a second group, periodic comets, which are observed at regular intervals of time, but not longer than a few hundred years. And the best example, probably the most famous, is Halley's Comet. Again, there is coma, there is the ion tail, and there is slightly curving dust tail. In 1704, Edmund Halley used the Newton's mechanics that was basically just put forward to calculate the orbits of comets. You could have a certain amount of data from the observations. You can have the data on a part of the trajectory, and from that you can, applying the Newtonian mechanics, his law of gravitation, you can actually calculate the orbit. And what he found was that the comets that were previously observed in 1456, 1531, 1607, and 1682, that they all have the same orbit, and the orbital period of about 75, 76 years. And he correctly concluded that that must be one and the same comet. If the orbits are identical, it must be one and the same object that is reappearing every 75, 76 years. So he predicted that the next appearance was going to occur in 1768, and he was right. Halley's Comet was observed again at that time. Now, before that, that was actually a scientific approach to analyzing of what is going on in the sky. In the past, the appearance of a comet was considered as an omen. And here are some of the previous appearances of Halley's Comet. Of course, there are records. They didn't know at the time that it's basically one and the same object. It appeared in 66 AD, and its appearance was taken to foreshadow the siege and destruction of Jerusalem by the Romans. Then its appearance in 1451 AD signaled the defeat of Attila the Hun in the battle with the forces of Western Roman Empire on the Rhine River. Then When it appeared in 1066, it was taken to foreshadow the Norman conquest of England. And then 1456, there was a threat that the Europe might be invaded by the Ottoman Turks. So I think it's in the human nature, these things don't appear every day. They appear, and then stuff happens all the time, good things, bad things, and it's in our nature to somehow tie that spectacular event with some usually bad event. Okay, so now let us look at some physical properties of comets. Here is a photograph of a nucleus of a comet, and you can see there are jets of gas and dust shooting out of the nucleus. And its structure is similar to what often people refer to as a dirty snowball. It's a mixture of ices, water ice, frozen ammonia, and frozen gases like methane and CO2, and small amounts of rock, silicate rock. So that's the composition of this nucleus. Here is a diagram illustrating the structure of the comet nucleus. Here are these pockets of ice, and then rocky material is dispersed in between. The surface is usually covered by carbonaceous, that is carbon-rich compounds, and as a result, the surface appears to be dark. It has a low albedo, low reflectivity. And then, of course, as a comet starts approaching the sun, it receives more and more solar heating. The material heats up, and then you have these jets of vapor. These ices are vaporized, and also of the dust. It turns out that the tails start developing only when a comet or the nucleus approaches the sun to within 4 to 6 astronomical units. Usually when it crosses the orbit of Jupiter at about 5.2 astronomical unit, then it starts developing its tail that becomes brighter and brighter as the comet gets closer, because the nucleus is receiving more and more heat, and more stuff is evaporating. So here is a diagram illustrating what is going on when a comet or the nucleus gets close enough to the sun. The dashed line indicates the comet's orbit. Here is a coma. In the middle of it is the nucleus of the comet, and then we have the ion tail, and we have the dust tail, and it turns out that there is a large hydrogen envelope that you cannot see really. So as I mentioned before, the nucleus varies in size from one comet to another, between about 1 to the largest one is 40 kilometers across. The coma is enormous in size. Its diameter is anywhere from 100,000 to 1,000,000 kilometers across. Now, as I said at the beginning, the ion tail consists of charged molecules. They are charged because some electrons have been knocked out by radiation, and they are pushed away from the sun by the solar wind and by radiation pressure. And then dust tail consists of larger particles, and they are pushed away by radiation pressure, but because of their larger mass compared to these small charged ions, these dust particles move slower, and as a result, their trajectory is such that it gives that curved shape to the dust tail. Now, it turns out that the orbits of most comets are not in the plane of the ecliptic, okay? As illustrated in this diagram here, the orbit can be at very large angle relative to the ecliptic. And there are two regions that we will discuss shortly where the nuclei reside. It turns out that there is a vast region called Oort cloud from about 50,000 astronomical units away from the sun up to 100,000 astronomical units away from the sun. And in this region, the nuclei move at random directions. And for some reason, one of them gets kicked to the inner part of the solar system and will become a comet that we could see, right? Note also that the orbits are highly elliptical. That was actually first realized by Halley when he calculated their orbits using the Newton's laws. He realized that these things move along highly elliptical orbits. And then there is a second source of comets, and this is a source. So Oort cloud is the source of long period comets. And the second region from about beyond the orbit of Neptune at 30 astronomical units to maybe about 60 astronomical units, where the nuclei of short period comets reside. So the nuclei of long period comets sit in the Oort cloud, which is much farther away than the Kuiper belt, although it's quite distant. It's beyond the orbit of Neptune. Note also that the orbits of comets in the Kuiper belt basically are in the plane of the ecliptic. So the nuclei in the Oort cloud move in all directions like bees in a beehive. The nuclei of comets that are part of the Kuiper belt, they are moved in the plane of the ecliptic, right? And fairly circular orbits. So here is a schematic description of what I was saying. There is Kuiper belt from about 30 astronomical units. The outer radius may be 60, so the diameter, the outer diameter is 120 astronomical units. And then the Oort cloud extends from 50,000 astronomical units to maybe about 100,000 astronomical units. So the nuclei of long period comets or non-periodic comets reside in the Oort cloud, and the nuclei of the short period comets, they reside in this Kuiper belt. So how do we know this? In the 90s, astronomers using the Hubble Space Telescope have actually detected 20-odd-something objects in that region that we refer to as Kuiper belt. There are also dwarf planets there. Pluto is a Kuiper belt object, really, and so is UB313, that is later on named as Eris, and its discovery caused the demotion of Pluto from the status of planet. So how do we know this? Well, let's see how far the gravitational influence of the sun extends, being significant in the sense that it can hold on to the objects so that they really revolve around it. And it turns out that the reasonable estimate is that sphere of gravitational influence of the sun is roughly 1/3 of the distance between the sun and the nearest star, right? So if this is sun and this is the closest star, then about 1/3 of this distance between the two stars describes quite well a region where the gravity of the sun dominates over the gravity of the other star, because points in this region are closer to the sun. Okay? So if you recall that the closest sun is at about 4.2, 4.3 astronomical unit, the third of that is roughly 1 light year, or 60 astronomical units. Okay? So that's why astronomers think that there is that region between 50 and 100 astronomical units where objects are still under the influence of sun's gravity and are revolving around it. The plausible scenario about the origin of the comets is something like this. Materials like water, methane, ammonia, CO2 can form solid particles only beyond the frost line, which is at about 5 astronomical units in the solar system. Okay? So, because we know their composition, they are made out of ices and some silicate material, and silicate rocks could have formed anywhere, close to the sun, far away, then they most likely form in the outer region of the solar system beyond the distance of Saturn and Uranus. At that time, when this material formed, it orbited the sun in the same plane as planets or protoplanets. The planets were still forming at that time. They were not already formed, like they're not like they are today. So as the outer planets grew, right, they were becoming more and more massive. They sucked in the hydrogen and helium from these outer parts of the solar system. Their mass really grew. They became giants, in particular Jupiter and Saturn. They were able, through their gravitational influence, to kick the nuclei that were initially orbiting in the same plane at great distance from the sun at random directions. And this can occur through so-called slingshot effect. It turns out that if a comet approaches a massive planet like Jupiter at some speed, it will whip around it, and it will end up moving in the opposite direction at the speed which is the sum of its initial speed and twice the speed of Jupiter. Okay? So it would be accelerated and launched at a great speed away from the sun. In fact, this slingshot effect is often used by space explorers. One of the probes that was launched in September of '77, Voyager 1, it was actually, the plan was to use it to study Jupiter and Saturn, and they sent the first beautiful close-ups of these Jovian planets. But then the idea was to actually send them out of the solar system. So the engineers, the scientists, they used this slingshot effect to increase the speed of Voyager so that its speed is great enough so that it will eventually leave the solar system. And indeed, just at the end of the last year, the data showed that Voyager 1 is still sending signals that basically it has exited the solar system. Right now, Voyager 1 in 2013 was at about 125 astronomical units away from the sun, right? So it was even beyond the Kuiper belt. It will continue sending signals for some time, but eventually the batteries will run out and it will become silent. So through this kind of slingshot effect, after a few billion years, most of the nuclei from the disk, the outer edges of the disk, were kicked out in random directions, and they formed the Oort cloud. Those comet nuclei in the outer edge of the disk that were out of gravitational reach by planets like Jupiter stayed behind, forming the Kuiper belt, much closer to the sun. So the question is, okay, fine, but how can a nucleus of a comet that is at 50,000 to 100,000 astronomical units away from the sun, how come all of a sudden it's kicked towards the sun, right? And how it becomes a long period of comet. And the likely scenario is that it is probably pushed in by a passing stars. Over millions of years, there could be a star that passed not far away from the outer edges of the Oort cloud. So suppose that we had a star, or rather a nucleus that was initially moving within the Oort cloud. If a star passed nearby, it would exert a gravitational pull on that thing, changing its trajectory. It would all of a sudden be redirected into the new orbit and would pass through the inner part of the solar system and close to the sun. What is the destiny of these things? Well, a long period comet might survive a trip around the sun and return back into the Oort cloud. Short period comets, such as Halley's Comet, they do not live very long. They might survive maybe 1,000 passes around the sun. And the reason for that is that every time they pass close to the sun, they lose about 10 million tons of material every day. So their mass decreases with each passage around the sun, right? So they will basically disappear. And their orbit could change. They could crash into the sun. And indeed, many comets collide with the sun. And here is a series of photographs of a comet. Here are the blow-ups. This is its trajectory as it is on its way to collide with the sun at blow-ups of a comet at different stages along this trajectory here. Some could actually strike a planet, and this is a spectacular photograph of comet Shoemaker-Levy that crashed into Jupiter in 1994. And you see what happened. The great tidal force produced by the Jupiter, it's a very massive planet, and therefore, as we discussed earlier, the tidal influence of Jupiter is enormous. The nucleus actually broke up in pieces. It formed a train, and each piece eventually landed on Jupiter. It crashed into Jupiter, okay? Or a comet can actually its orbit can be changed by the Jupiter. So instead of being a long period of comet, it all of a sudden becomes a short period comet. The gravitational pull by Jupiter changes its orbit so that instead of being a long period of orbit, all of a sudden it becomes a short period orbit comet.